All right, so our last section in chapter 6 deals with learning about atomic size, ionization energy, and electron affinity for the elements. So many properties of elements vary periodically as the electronic structure of the elements changes. These properties govern the chemical behavior of elements. So these periodic properties include atomic radius or atomic size, size of atoms and ions, ionization energies, and electron affinities. And so because the periodic table is organized in such a way, we can predict, for example, the size of one atom being larger than the size of the other, or the size of an ion, one ion being larger than the other. We can also predict, because of the location of the elements on the periodic table, we can predict ionization energies. We can predict electron affinity for different elements, and we can rank them. Okay, so these are some of the skills you're going to have to learn how to do. The first thing to do is to memorize the definitions for these three things. Okay, what is atomic radius? What is ionization energy? What is electron affinity? What does that mean? Okay, and then understand the periodic trends on your periodic table. Now, towards the end of the chapter, I've added a slide here that shows you the trend. So you might want to jot this down on your periodic table. Whether it's metallic or non-metallic, you probably already know this, but we're going to talk about this towards the end of the lecture. But we're going to be going through each of these three things: atomic radius, ionization energy, and electronegativity. And we're going to talk about the trends on the periodic table. Okay. And so if you have these on your periodic table, you can use them to study from, but you really need to memorize them, because I will not let you have periodic trends sketched on your periodic table when you come in, okay, for the test. So just keep that in mind, that you have to memorize the trends. Now, I'm going to explain to you why the trends are what they are. And so, because of this information, hopefully you should be able to remember it by just thinking about what you're talking about and in how that relates to the elements that we're dealing with. And for example, does the ionization energy go up or down from left to right? And why does it do that? So if you understand the why part, then the other parts should sort of fall into place in that respect. Okay. All right, so I'm lost here. All right, so these three things are the focus here of this section. So let's start with atomic radius. So this is something you should memorize here. What is the definition for covalent radii? So the covalent radius is defined as 1/2 the distance between the nuclei of two identical atoms when they are joined by a covalent bond. So it's basically half the distance between the nuclei of a diatomic molecule. Diatomic molecule is two identical atoms. It's half that distance. Distance between the two nuclei, half of that distance is the covalent radius for the atom. Okay. So down a group, the principal quantum number n increases by 1 for each element. The electrons are added to a region of space that is increasingly farther from the nucleus. The size of the atom increases down a group. Okay. So if we think about atomic size, what is the atomic size of an atom? Well, if you think about even an individual atom, even though the definition is two adjoining identical atoms, you can think of it in terms of a single atom. Okay, so let's compare the size of hydrogen. We're going to draw two board models here. The size of hydrogen, okay, versus the size of, let me see here. What do I want to use? Hydrogen versus sodium. Okay, so sodium, let's see. Hydrogen, we know it has one electron back here. It has one proton and one electron. Okay, and then sodium has, it has 11 protons, so it has 11 electrons, so 2, 8. So it has 3 shells, okay? One valence electron, hydrogen has 1 shell. So obviously the size of sodium is larger than hydrogen, right? So as we move down a group, the size of the elements increases. Cesium has 6 shells. Francium has 7. Okay, so more shells, larger size, right? So cesium is the largest. It has 7 shells. 1, 2, 3, 4, 5, 6, 7. It's very large, okay, compared to elements above it, okay? So that pretty much makes common sense if you think about it, right? Atomic size increases as you go down. That's a trend, okay? So going back to our picture here. For atomic radius, now these arrows point to increasing value. So every time it's pointing towards in a certain direction, it's the assumption here is that value is increasing as we go towards the arrow. So as we go from up top to the bottom, the atomic radius is increasing. All right, just like I explained. All right, so let's look at atomic radius going from left to right. So notice how it's written here. From right to left, the atomic radius increases. So why is that? Now that is a little bit harder to explain. So we're going to go through some slides here and where they try to explain that to you. Okay, it's my recommendation that you don't just memorize these things, because you need to have a reasoning and rationale why. So when you go on the test and you start to panic, you're not going to remember gibberish, but if you remember things that make sense to you, then you can, if you know the why behind it, then you'll remember what the trend is. All right, so down a group, atomic radius increases. Okay, so down the periodic table it goes up, atomic size increases. Okay, so in order to understand the trend of the atomic radius increasing from right to left, okay, we have to learn about effective nuclear charge. Okay, so effective nuclear charge is a pull exerted on a specific electron by the nucleus, taking into account any electron repulsions. So for example, for hydrogen there is only one electron, and so the nuclear charge and the effective nuclear charge are equal. Okay. But for all other atoms, the electron of interest are particularly shielded from the pull of the nucleus by the other electrons present. Okay, so the electrons are partially shielded from other electrons because if an electron is in front of another electron, it's shielding the pull of the nucleus. Okay, so here I have this big old nucleus that the electrons are attracted to. Right, if I have an electron here, electron in a higher energy level here, okay, this guy is shielding, okay, it's kind of getting in the way of this guy here, and so the effect here is going to be, its attraction to the nucleus will be somehow, is going to be affected by electrons that are in front of it. Okay, they can't feel that effective pull and attraction to the nucleus as well, because you have shielding here, electron shielding. So core electrons are adept at shielding, while electrons in the same valence shell do not block the nuclear attraction. So let me draw this picture again. All right, so here I have some core electrons, okay, here. And then I have some electrons, some valence electrons here, okay. So, these electrons here are not going to be shielded by electrons in the same shell. Okay, they're the same distance away, so it's not going to happen. Core electrons are going to shield electrons that are on higher energy levels. Okay, they're going to shield them from the effective the pull of the nucleus. Okay, so these guys have a greater pull attraction for the nucleus compared to electrons that are further away. Okay, so the energy levels of the electrons further away are higher than that of electrons that are closer to the nucleus, core electrons. So each time we move from one element to the next across a period, okay, the effective nuclear shielding is going to increase by 1, but the shielding increases only slightly due to electrons being added to a valence shell. So what they're saying is when we go from left to right on the periodic table, let me go here. As we go from left to right on the periodic table, okay, since we're adding electrons to the same energy level, okay, it's sort of like we're adding electrons here. We keep adding electrons here. Your shielding isn't going to be affected, right? But what you have to remember too is the number of protons are also increasing. So if I add an extra electron, I have to add an extra proton, okay? The effect of protons, one proton is so much greater than one electron because one electron's mass is very small, 2,000 times smaller than a proton. So what ends up happening, even though you might have some slight amounts of electron repulsion because you're adding electrons on the same energy level, because you're adding protons as well every time you add an electron, basically the electrons are able to move in closer. Okay, so as you go from left to right on the periodic table, the size of the atoms becomes smaller. Okay, because you're adding electrons, but you're adding protons too. Okay, and because that one proton is like going to have a very large effect compared to one electron. Okay, and so you're going to get a smaller atom in that case, and so that explains why as you go from left to right, the size decreases. Okay, so that's why the arrow is pointing in the opposite direction. This is an increasing atomic radius for atoms that have fewer protons and electrons. And so atomic radius is smaller. On the on the right-hand side than it is on the left-hand side. So what's the largest element? That's something that's good to remember. So that should be francium here. It's the largest. Okay, it's at the furthest down, and it's to the left, so it's the largest element. All right, so that's the trend with atomic radius. We have some more information too here. So when we talk about covalent radii across a period, here's their explanation. The stronger the pull, the higher the effective nuclear charge is experienced by the outermost electrons, drawing them closer to the nucleus. The size of the atom decreases across a period. What we said. All right, so we talked earlier about covalent radii. And so what is the radius of a fluorine atom, for example? So it's half the distance of two adjoining nuclei for identical atoms. And so here we have two fluorine atoms. The distance between the nuclei is 128 picometers. And so if we divide that by 2, that's 64 picometers. That would be the radius for fluorine. Same process for chlorine here. It's the distance between two adjoining nuclei is 198 picometers. So divide that by 2, and that's 99 picometers. That's the radius of a chlorine atom. Okay, same process for bromine and iodine. So that's how you would calculate the radius of an atom. Now this picture pretty much shows you what the trends are now. These are periodic trends when we look at the graph we're about to look at. you might say to yourself, well, it's not going to show up. Okay. There's some exceptions, and that's true. So don't get bogged down by the exceptions. In chemistry, there are a lot of exceptions. I'm not going to be mean to you and give you a bunch of exceptions on the test and expect you to memorize those things. I'm pretty fair when it comes to those types of things, unless I mention it specifically. Don't worry about exceptions so much. All right, so here's a picture of, let me zoom in here so you can see this better. The sizes of different elements. And so here we can see as you go down the periodic table, the size of the atom gets larger. And that's exactly what we said with the trends. Of course, you're probably saying to yourself, well, I see some exceptions. That one looks a little bit bigger than that one. But don't really stress yourself out about that. Just take my word for it, okay? We're going to be talking about some commonalities. We're not going to talk about exceptions so much. Don't worry about it. All right, as you go from left to right, we said that the size of the atom gets smaller. You can see that for the most part, it's getting smaller as you go from left to right. It's really hard to tell this picture. But for the most part, the sizes are getting smaller as you go from left to right. All right. And so they're just reminding us the radius of an atom is defined as 1/2 distance between a nuclei and a molecule existing with two identical atoms joined by a covalent bond. Atomic radius for the halogens increases down the group as n increases. Covalent radii of elements are shown to scale here. The general trend is that the radii increase down a group and decrease across a period. So they get smaller across the period. All right, so here's that graph that I was referring to. You're going to see some little blips. For the most part, though, you see the radius for lithium is higher. And as you go across period to neon, the atomic radius gets smaller. Of course, let me go back here. Starting with hydrogen, helium gets smaller, it goes down. Okay, then you get then the next period, you have lithium to neon, and you see a downward trend there. And then sodium to argon, and you see a downward trend there. Just like we said this atomic size decreases as you go from left to right, and that's what we're seeing here as you're going from left to right, from sodium to argon, from potassium to krypton. See how it's not exactly perfect. It doesn't go completely down. There's some, and they're saying that here. Well, these are transition elements, so they're kind of weird. They're hard to model. So here we have rubidium going down, xenon, cesium going down. So in the most part, these trends are helpful when you're ranking elements that aren't right beside one another. Okay, and so that's the type of questioning you're going to have on your test. All right, so what about ions? How does that affect the size of an atom if it becomes an ion? So an ionic radius is measured used to describe the size of an ion. A cation always has fewer electrons and the same number of protons as the parent atom. So as electrons are removed from the outer valence shell, the remaining electrons experience a greater nuclear effect charge and are drawn even closer to the nucleus. So as a result, a cation is always smaller than the atom from which it was derived. But here's a simple way to remember that. If I compare sodium to sodium plus, an ion, its parent atom to the ion. So it has 11 electrons. Okay, so it has 3 shells. So here it has its valence electron. Sodium plus is only going to have 2 shells. It's not going to have a valence electron because when it loses its valence electron, it loses its entire shell there. So the next electrons, which were core electrons before, okay, it's going to be smaller. It only has 2 shells and not 3. Okay, you're going to see that with all group 1 metals. Or anytime, even for magnesium, for example, it has 2 valence electrons. When it loses those 2 valence electrons, it still has those inner core, it's going to be smaller than it was before. Okay, so that's something you just have to sort of memorize. Cations get smaller. Well, it makes sense. You're taking an electron away. It's losing an entire shell. It's going to be smaller. Okay, atomic radius, it will be smaller. All right, so what do you think about anions? So an anion has more electrons and the same number of protons as the parent atom. So this results in a greater repulsion among the electrons and a decrease in the effective nuclear charge. So this causes the valence electrons to be farther from the nucleus. An anion is always larger than an atom from which it is derived. Okay, so if we talk about fluorine, okay, fluorine has 7 valence electrons. All right, when it adds another electron, it's going to have this added extra electron is going to cause F minus to become larger because of electron repulsion. 3. All right, so F minus is always larger than F. Okay, so an anion is always larger than the parent ion. And so this is a nice picture that represents that. Here are some actual values for the radius of aluminum versus aluminum 3+. It's lost 3 electrons here. Its size is smaller than that of the parent atom because it's a cation. And the opposite is true for anions. Here we have the radius for sulfur, and then sulfur 2- is a lot larger because it has gained electrons and its atomic radius has increased. All right, so then there's a concept called isoelectronic elements. And so atoms and ions, we've already kind of talked about this a little bit. We didn't talk about what the official name of it is, but when we talked about sodium being sodium versus sodium plus versus the electron configuration for sodium versus sodium plus, and we noted that sodium plus has the same electron configuration as neon. Okay, and that a lot of these, like group 1, group 2 elements, group 3 elements, they form +1, +2, +3 ions because they have and want the same electron configuration as in their nearest noble gas, which is neon. The same is true for nitrogen or oxygen or fluorine. When they gain 1 or 2 or 3 electrons, they have the same electron configuration as that of neon, a noble gas. So these examples are examples of isoelectronic elements. They have the same electron configurations as other elements, okay, and a lot of times they're ions that have the same electron configuration as a noble gas. And you see that here in the second example as well, ions, and then the one that's not an ion is a noble gas. So for atoms or ions that are isoelectronic, the number of protons determines the size. The greater the nuclear charge, the smaller the radius in the series of isoelectronic ions and atoms. Okay. So next we need to talk about ionization energy. So first of all, what is ionization energy? Ionization energy is the amount of energy required to move the most loosely bound electron from a gaseous atom in its ground state. Okay, so there's some specification to this definition. So if you remove an electron, one electron from the first electron from an atom, it's referred to as the first ionization energy. So here I have an atom. I use some energy to remove this neutral atom's one electron from this neutral atom to make it a positively charged atom, and its electron that was removed, and that's referred to as IE1, i.e. ionization energy needed to remove the first electron from this neutral atom. And then what is the second ionization energy? Well, that's the energy required to move the second most loosely bound electron to, that's called the second ionization energy. So here, the second ionization energy is the energy required to remove a second electron from a cation in this case. It has a +1 charge. Okay, we removed its second electron, and the amount of energy it takes is referred to as the second ionization energy. The energy it takes to remove a second electron from an atom. And then the energy required to move a third electron from an atom is referred to as a third ionization energy. Okay, and again, we would be starting with X2 plus. Okay, how much energy does it take to remove a third electron? That's referred to as a third ionization energy. So, ionization energy in general is just the amount of energy it takes to remove an electron from an atom. So, what are some of the trends? Okay, so energy is always required to move electrons from atoms or ions. So, ionization processes are endothermic, and ionization energy values are always positive. So, ionization energy is related to atomic radius. Okay, so as size increases, the ionization energy decreases. The larger the atom, the easier it is to remove its electron. Now, does this make sense to you? Well, if you think about it, we've been talking this whole time about electrons and how when an electron is really far away, it has more energy. Okay, when we say it has more energy, it really has more energy to do more things, right? We know like valence electrons, for example, they're the ones involved in chemical reactions. They have higher energy values. They're more likely to be able to be removed or transferred, that sort of thing. Okay, so when we think of it in this way, it's kind of easy to think about an atom that's very large compared to an atom that's very small. Let's compare these two things. I have something like lithium. Okay, so it has 3 valence electrons. And then I have something like, let's do potassium. It has how many shells? 1, 2, 4. All right, so lithium versus potassium. So here you see the 4 different shells there, and I'm just putting in electrons randomly here. Actually, there should only be 1 on the outermost, okay? Anyway, so for potassium, it has more protons too, all right? But the question is, why would it be easier to take an electron for potassium than it would be from lithium? Look how close the electrons are to the nucleus compared to electrons that are out here. Remember, the electrons that are being removed for ionization energy are the most, what they say, the most loosely, electrons that are loose, that are basically available. They're going to be valence electrons, okay? They're not going to be core electrons. So what we're saying here is that it's easier to remove the electron from a large atom than it is from a small atom. Now, I have an analogy that I use with the high school kids. If you play basketball, you can kind of understand this analogy, I think. So if I have a player that's really bouncing the ball up close to its body versus a player that has that's bouncing the ball like really far away, like they have their arm outstretched and they're bouncing the ball like really far, like with their arm completely stretched out instead of bouncing the ball really close to their body. It takes so much less energy to take the ball away from somebody that's dribbling the basketball really far away from their body than it is from someone that has the ball that's real close to their body, right? So their body is like the nucleus, okay? Same thing with ionization energy. It takes less energy to remove the electron, just like it takes less energy to remove the ball. Someone that's dribbling it far away from their body compared to someone that's dribbling the ball close to their body. So it's easier to remove an electron from a larger atom than it is from a smaller atom. Same idea. All right. So that's good because we know the trends of atomic radius, right? We already know that. So that's good because then we can kind of understand that in a way of trying to find where I'm supposed to be here. So because we know that the size affects ionization energy, as the size increases, ionization energy decreases. It's easier to remove electrons from atoms that are large. So first ionization energies, the trend is they decrease down a group. Okay, does that make sense why they would decrease down a group of first ionization energy? So here we have ionization energy. They decrease going down a group, okay? Or as you can see here, here again, the arrow is pointing to increasing values, all right? So as you go up the periodic table, the ionization energy increases because the size of the atoms gets smaller, okay? So that makes sense. All right, now, as you go from left to right, ionization energy increases. So why is that the case? Well, if you think about the type of elements you have going from left to right, you're increasing valence electrons, right? So remember when we talked about how group 1 elements give away their one valence electron, group 2 elements give away their 2 valence electrons, group 3 give 3. When you get to a point where you have 5 valence electrons or 6 or 7, they always form anions. They always gain electrons. So why is that? That's because they almost have 8 valence electrons, right? Remember the octet rule, they want 8 valence electrons, they almost have it here. So what's going to happen is it's going to take a lot more energy to take an electron away from oxygen, for example. It already has 6 valence electrons. It's going to take a lot more energy to take it away than it would be for sodium. Sodium only has 1 electron. It wants to give it to you, so its ionization energy is going to be small. It's not going to take much energy to remove that electron because that's what it wants to do for sodium. But for something like even fluorine does not want you to remove its electron. It has 7 valence electrons. It wants 1 more. It doesn't want you to take it. So the amount of energy you're going to have to expend to remove that electron is going to be a lot more than, any kind of metal here. In general, the non-metals form anions, and so they have higher ionization energies compared to that of metals, which tend to give their electrons away, and so they have lower ionization energies. All right, so knowing that, let's see where we are here. So first ionization energies, they decrease down a group, they increase across the period. So there are some deviations to this trend, and it depends on, they're just talking about first ionization energies. What about second or third? That becomes more complicated. Okay, so here we see first ionization energy for elements in the first 5 periods that are plotted against their atomic number. So here we see hydrogen and then helium, and so the ionization energy is greater for helium than it is for hydrogen. Would you expect that? Yes. Why? It's a noble gas. It has 2 valence electrons. It's as much as it wants, so it's going to take a lot of energy to remove an electron from a noble gas than it would be from an atom that only has 1 electron. And hydrogen forms +1 ion, so it's not going to take much energy to remove that 1 electron. It wants to get rid of it anyways. So you notice the trend here, noble gases having high first ionization energies. Makes sense to me. Now, what has the lowest here? Group 1 elements. Does that make sense? Yes. Again, why? They want to lose that 1 electron. Now, what if it was a second ionization energy values? Would this chart be the same? And it would not be the same. Because although lithium wants to lose 1 electron, it doesn't want to lose 2. Because once it loses 1, it has the same electron configuration as that of helium. So it does not want to lose another electron once it gets to that point. So the second electron, or the second ionization energy for helium would be a lot larger, or for lithium would be a lot larger than this value here. It wouldn't be the smallest. It would be it would be almost like a noble gas again. Okay, because it wants to lose 1 electron but not 2. Okay, and so here you see the trend going up as you go across a period, which makes sense. You're adding electrons, so when you try to take one away with ionization energy, then it ends up, you're having an increased amount of energy needed in order to remove that one electron. All right, so here we have actual values of first ionization energies for all the elements of the periodic table. And so you're going to, don't get caught up on some inconsistencies here in the trend. Okay, so for the most part, it's going to be fine. Just use your trends, and trust me, I'm not going to, give you exceptions, so don't worry about that. Just believe me when I say to remember and memorize your trends for your periodic table. All right, so here we see deviations in ionic or ionization energy trends. So here for beryllium has a higher first ionization energy than boron. So here they're trying to explain why. So electrons moved for during the ionization of beryllium is in an S electron. Okay, the electrons removed during the ionization of boron is a p electron. So the energy of a subshell increases as L increases. That means that the S electron is harder to remove from an atom than a p electron is in the same subshell. So here, oxygen has a lower first ionization energy than nitrogen. So removing one electron from oxygen will eliminate the electron-electron repulsion caused by pairing the electrons in the 2p orbital. This means that removing an electron from oxygen is more energetically favorable than removing an electron from nitrogen. Removing an electron from a cation is more difficult than removing an electron from a neutral atom because of the great electrostatic attraction to the cation. If you think about it, the electrons are closer to the nucleus. Okay, they it takes greater energy to remove them than it would be for a neutral atom. Likewise, removing an electron from a cation with a higher positive charge is more difficult than removing an electron from an ion with a lower charge, because why? Those protons affect the attraction there. Thus, successive ionization energies for an element always increases. All right, so here we see a chart that sort of demonstrates that. Here we have ionization energy for the first electron versus the second versus the third versus the fourth, fifth, sixth, and seventh. And you notice that here ionization energies are increasing, okay? So that's the general trend. The more electrons you remove, the higher the energy it takes to remove it from cation, which we saw earlier. The second ionization energy, for example, you're removing an electron from a +1 cation. Here, IE3, you're removing it from a +2. Here, you're removing it from a +3. Here, you're removing it from a +4, and so on. So successive ionization energies, at some point there's always a large increase in ionization energies for an element. This large increase corresponds to removal of core electrons, which are harder to remove than valence electrons. So scandium and gallium both have 3 valence electrons. The large increase in ionization energy occurs after the third ionization. All right, and then the last type of thing we're going to talk about in this section is called electron affinity. Okay, or you might see it as and refer to it as electronegativity. Okay, so electron affinity is the energy change for the process of adding an electron to a gaseous atom to form an anion. All right, this process can be either endothermic or exothermic depending on the element. For some elements, energy is released when the gaseous atom accepts an electron. Has a negative electron affinity, and then for elements, energy is required for the gaseous atom to accept an electron, so it has a positive electron affinity in that case. All right, so variations in electron affinity. It becomes easier to add an electron to an effective nuclear charge of the atoms increases, if the charge of the atoms increase. Electron affinities become more negative across a period. There are deviations from this trend. All right, so here let's look at the trends for electron affinity as you go from the bottom up. Electron affinity increases. Okay, so we notice the size of the atoms decreases, electron affinity increases. As you go from left to right, the electron affinity increases, and the most electronegative element, okay, is referred to as is fluorine. Okay, fluorine has the highest electronegativity. Okay, so deviations from electron affinity trend. The noble gases, group 18, have completely filled shells, and incoming electrons must be added to a higher energy level. Okay, so with noble gases, since we're talking about electron affinity, they have no electron affinity. All right, they do not want an electron at all, so they're sort of excluded from talking about electron affinity. They would have zero electron affinity. Group 2 has filled in S subshells, and so the next electron added goes to a higher energy level in P subshells. Group 15 has half-filled P subshells, and the next electron must be paired with an existing P electron. In all these cases, the initial relative stability of the electron configuration disrupts this trend in electron affinity. Okay, so here we can see values for electron affinity values for selected elements. Here we see the noble gases have positive values, meaning they don't want electrons. Here, you don't see any for transition metals, but you see the trends here going from left to right increases electron affinity, and going from the bottom up, the electron affinity also increases. Okay, if you think about it, going towards the nonmetals, they want electrons, so of course you would expect an increase in electron affinity. From the bottom up, you would expect electron affinity from atoms that are smaller, and because they're able to attract the electrons because they're smaller atoms, so the nuclear charge has a greater pull on those electrons. So they want electrons more than a larger atom, because larger atom, its nuclear charge attraction is not as great as that of smaller ones. So anyways, sketch out these trends. I do have a couple examples for you. Let's see here. Very quickly.